Good. Hi, everyone. Thanks for coming today. We're talking about how hot it is, so we're gonna have a talk about snow. But I'm really grateful to be able to introduce the speaker today, Dr. Andrew Schwarz. Dr. Schwarz is the lead scientist and station manager at the UC Berkeley Center for Snow Lab in Donner Pass, California. He earned his PhD in atmospheric science in 2021 from the University of Queensland, where he studied hydrometeorology of the Australian Alps and the impacts of bushfire on snow and vegetation. And his current role at the Snow Lab, his work spans research, operations, and outreach. And we'll hear more about this in the talk, but the Snow Lab is a hub for snow information in the northern Sierra Nevada, the region, as well as around the country and the world, and is a crucial source of insight into water supply issues and climate change. In addition to research and operations work, Dr. Schwarz is very engaged with public outreach and policy, including very delicious events with snow cones around the top of the region, and has written about drought and snow in the New York Times, and articles covering the Snow Lab in the past winter have numbered over 3,500 articles in terms of these coverage of the lab. So it's also very famous. And has very strong opinions about pizza restaurants in the taco in that area. So please join me in welcoming Dr. Schwarz.
Cool, thank you guys. Yeah, no snow cones today, unfortunately, but it's funny you mentioned that. This year we realized that kids don't care about snow unless they get to eat it afterwards. But yeah, so I run the Central Sierra Snow Lab. I'm Andrew Schwarz. I've been at the Snow Lab for about 2.5 years. And first, sorry for starting 5 minutes late. The plan, I had a guest lecture right before this that was going to go right at 3:30, and it turns out a fire drill interrupted it, so we got out early anyway. So anyway, we'll have plenty of time to chat afterwards too, but I'm going to talk about the current state of water and snow in California and the Western US. Realistically speaking, it's kind of a high-level talk, but there's a lot of points in there that kind of discuss some of the challenges that we face and where we are at with a turning point with climate change. I get the irony of making a pun in a title that says "Snow Laughing Matter." Okay, I get it, but I thought it was fun to put that in there. I'm anything but serious. So I'm starting my slides a little bit differently than I normally do. I work with a nonprofit called Protect Our Winters. And they always have really inspirational presentations. So I'm going to take a slide out of their book. And so as a thought experiment, think about the last interaction you actually had with fresh water. Could have been just now as you're taking a drink. It could be this morning when you took a shower, but hopefully on a 92-degree day, it's more recent than that. So think about that interaction with water, okay? And then think about how often you actually think about where that water comes from when you turn on the tap or use the restroom or go swimming for your recreation and for your workout that day. And chances are, if you're like me, I work in the hydrology world, but I still don't think about it that frequently. I know the water's coming out, I know I'm using it for various things, but we don't think about it enough. And that is an important thing because that leads to a little bit of separation between us and realistically our most critical resource, right? We know it comes out when we need it, but in terms of overall thinking about things, chances are you're not using every aspect of this graphic. This was released by the US Geological Society earlier this year as a more comprehensive water budget. This is the water cycle, right? It's no longer cloud rains, rain goes into stream goes into ocean, and then back into clouds, right? It's a lot more complex than that. And chances are, for all of us, we're not thinking about this every time we turn on the faucet. And so that can lead to a few different things. First, we're all aware that we have recency bias, right? We tend to remember things that happened in the past, and those recently in the past, and those influence our decision-making. So when you think about this last water year, which is October 1st through September 30th, for those unaware, what are you thinking about? Chances are it's some of these images. I covered up my Lake Tulare in the middle with my wording, but that was Lake Tulare from a flight that I took to Arizona earlier this year. So a lake reappeared that's only been there a few times in the last several decades because of the flooding that we had in the mountains, the water that we had. On the right, that's a Hetch Hetchy Reservoir that was actually taken from my New York Times article celebrating that we actually had so much water that we were worried about it. It's funny, the swings that we get, right? Not enough water, everyone freaks out. Too much water, everyone freaks out. We needed a moment to just appreciate it, and look, a nearly full Hetch Hetchy. It was full after that. On the left, that's the snow lab. This image is 3 student researchers from UNR in a 16-foot deep snowpack. It is also what I call the photo heard throughout the safety world, because I got in a lot of trouble in LinkedIn safety circles about whether or not that needed to be shored up in the same way the soil would be, so they didn't get buried by the awful snowpack. Spoiler alert. OSHA says it's okay, but it did get me in a little bit of trouble. But chances are, if you're thinking about this last water year, you're not going to be thinking about the problems that we're facing with water. There are studies that actually show that if you're talking about climate change on a hot day, the majority of the people paying attention don't feel like climate change is as much of an issue. So today, we're all less likely to see, or more likely, I should say, to see climate change as an issue because it's hot. Tomorrow, if you're up on top of the mountain with me and it's a cool 37 degrees, probably not as much. But we have that recency bias. But of course, we are in a state of crisis with our water in the Western US. And there's a number of components that have brought us to this point. When we talk about these 2 plots, I'm not going to dive into them a lot, but effectively this was a study released by Williams et al. In 2022 that showed that going into that year, we were in the driest 22 to 23 year period in 1,200 years in the Western United States. So last year was big, but this is the overall trend. And it's not just a trend in the Western US, we're seeing this all over different parts of the world. And of course, that trend in drying, that trend in increasing drought means that we see more of these headlines. We see things like the largest fire in history with the Dixie Fire here in California, the East Troublesome Fire in Colorado that hopped the Continental Divide that was largely considered to be the biggest fire break you could imagine. And then you also have things like Lake Mead and Lake Mead and Lake Powell in the news about their record low levels, and the fact that we're basically having to toss water between them rather than allow them both to fill because we just simply don't have it. And of course, we have Salt Lake City and their close ecological disaster once the Great Salt Lake dries up and releases all that salt and various other pollutants into the atmosphere. But to take a step back and away from the doom and gloom for a minute, I think it's best to put all of this in a little bit of context. So for half the world, we depend on water from mountains. And for a quarter of the world, that water directly comes from snowpack. 2 billion people. So from the Swiss Alps in that left image to the Japanese Alps in the top right, to Reno, Nevada on the eastern side of the Sierra, we all depend on that snowpack. Bringing it back a little closer to home, when we talk about the Western US here, we get about 3/4 of our water in terms of runoff in the various areas of the Sierra Nevada, Rockies, and Cascades from snowmelt. So it's an incredibly important resource. And when we look at this image, you can see the outline of the Sierra Nevada with Lake Tahoe up there. You can see the Rockies on the right, Cascades up along the coast further north. And when you look at the overall area that's covered in snow compared to the amount of area that it's providing water for, it's massively disproportional, right? Now, don't get me wrong, this image was taken actually earlier this year. It was taken in May of 2023 after a record-breaking season. So it's not as big as it was in April, but this is still a record snowpack, so larger than it would normally be. So we're talking 3/4 of our water here in the Western US from snow. When we zoom into California here, again, this beautiful Sierra Nevada. I want to ask you guys a question. How much snow does California get in an average year? We're all friends. Say something. Doesn't matter what.
4 giraffes.
4 giraffes. Oh, that's on a record-breaking year, sir. On an average year. Half a giraffe. Okay. It's closer, actually. Oddly enough. Okay, so we have half a giraffe. We have 4 giraffes. Now, what was the thought process behind those answers? Because you heard me say 4 giraffes earlier, but why did you pick half a giraffe?
I heard that we had like 100 times the normal amount of snowpack in the like atmospheric river period.
So you derived your answer from 4 giraffes. Okay, fair. Well, I think a lot of us get stuck on a question like this, and this is the question that comes up time and time again when we talk to media outlets. Whenever it's around the April measurement for our snowpack, whenever it's around record-breaking seasons like this last year, they go, how much snow does California get in an average year? And that is an incredibly complicated question. And every time somebody asks me that, I go, because it's not a straightforward answer, right? There's this massive range of mountains, all different elevation, all different aspects that are covered in snow, and they all have different weather patterns. We're talking massive amount of area. At the snow lab, our average year right now is 360 inches. This year we got 754 inches, so 62 feet, 4 giraffes roughly. So big here, but the problem is spatially and temporally, it varies, right? And there's another big problem with this question. Does anybody want to take a whack at what that is?
Climate change.
Yes, it pertains to climate change.
Baseline of what is there.
Exactly. What is an average year? California, like many places in the world, doesn't do well with averages. I did my PhD in Australia. That is not a land of averages either. And so we get these wild swings back and forth, meaning there's really no such thing as an average year. We can extrapolate, we can do medians, we can kind of try to guesstimate, but we really don't have average years. And that leads to problems. Does anybody in here follow water news and know what happened with DWR in 2021? It's not, Marion? No? In 2021, DWR modeled an extra 700,000 acre feet. For those that aren't familiar, an acre feet is 1 acre with 1 foot of water on it. 700,000 acre feet. That's a lot of water. That is, and I've done the math, about 360,000 Olympic swimming pools, or enough Olympic swimming pools to cover 428 square kilometers. They modeled that much water coming down and replenishing their reservoir, so they did releases of the water that was already in there to that same amount. And that water never showed up, which meant that we had artificially created a drought through our own management of the water system, because we didn't understand where that water from the snowpack was going to go, because we had anticipated it coming into where we were. And that led to this. A lot of legislative sessions talking about the need to audit the California Department of Water Resources. And that brought us to an answer that was released just this last spring on what went wrong. Now, some insider information. I work with the group that stuffed up this forecast. And they basically blamed it on the fact that because of years of drought, we hadn't accounted for the correct soil conditions, and the soil acted like a big sponge and soaked up all that water, and we weren't ready for it. The bigger answer, and probably more accurate, in my opinion, is that our modeling techniques are chronically outdated. We are in a new world where physical models are able to be run in more and more rapid succession on supercomputers, like our weather models, our hydrological models. But that is assuming that all of our agencies that manage water actually adapt those models. There are still agencies throughout the Western US that use basic linear regressions. We have X amount of snow, we can expect Y amount of water. And that is based on averages that never really existed. And even if they did, they've changed, right? That 30 feet of snowfall at the snow lab, that's a recent average from 1991 to 2020. If you go back prior to that, it was a lot more. So we have all these outdated models, and it has led to these types of situations. Now, ultimately, the findings of that audit were that their models don't account for climate change and changes in the atmosphere, and therefore our water system. And because 3/4 of our water is comprised of snowpack, they're not accurately measuring our snow, and so they can't really model how well we're going to do. Now, to bring this to where the snow lab enters the picture, We are turning a corner in our water resources and weather and climate. We are now entering almost uncharted territory. It has been things that have been predicted to occur, but we're actually being hit with the repercussions, and we're struggling to keep up with what those are. Now, following World War II, the Army Corps of Engineers and the Weather Bureau came to a similar realization. They went, wow, we don't know really anything about our snow hydrology and climate in the Western US and how as it pertains to our water. And so they struck out to develop the Cooperative Snow Investigations Research Program with the aim of solving these problems. And I always think it's funny that they use the word solve, because if anything, we really just kind of identify them. I don't know how much we've solved. But the creation of the lab was at a similar point. They went, we need to find out more about how our water works at its most basic state, how we can forecast that to make sure that we're managing it properly. And so they developed the Snow Lab, which is one of 3 initial labs of its kind. There was one here, one in Oregon, and one in Montana. Any ideas on why we had 3? It's not Marion? No. So first thought, when you think about California, who's been to Montana? How is Montana's weather different than California's in the winter? Colder? Right. So we have different climatic zones, right? And snow is going to be different in those climatic zones. The physical processes are the same, but overall, we wanted to develop a comprehensive overview regardless of climate conditions. So that's why we created 3 labs. Or they created, they created 3 labs. So of those initial 3, only the Central Sierra Snow Lab exists now. But that's what led to the early creation of the Central Sierra Snow Lab. And this is it in all its glory, so to speak. It's just a 3-bedroom cabin out in the middle. Well, it used to be out in the middle of nowhere. Now I-80 is relatively close to it. But on the top floor, you've got 3 bedrooms with room to house 7 people. You've got a main lab floor where there's computers, data server, tech desks. In the basement, there's a wet chemistry lab. It's not glorious. It's just a cabin out in the middle of the woods. But there's been a lot of important science done at this lab. And it has been going on for a very, very long time. We've had a lot of development of physical properties of snow and what alter them. We've had a lot of development of best methods to measure that snow, including some that were very questionable at the time, like placing radioactive isotopes on the ground and then putting a Geiger counter above it on a board and then just letting the snow build up and looking at how the Geiger counter changed. And then once that fuel was spent, they would sled down the hill with it between their legs to take it to the truck. Bruce McGurk said that. He used to work in the lab, actually. So it's been going on for very long up there that we've been making these strides to try to make sure that we can manage our water properly. Over the last 3 to 4 decades, it kind of became, or I shouldn't say 3 to 4, over the last 3 decades, it kind of became more of a monitoring station and less focused on research. So we were really focused on monitoring weather conditions and adding bars to this plot. And what this plot is, it's the longest record in the world of annual snowfall and maximum snow depth. It goes all the way back to water year 1879, so fall of 1878. And the reason why we have this record is because the Transcontinental Railroad came up and over Donner Summit, not far from where the lab exists today. In fact, less than half a mile from where the lab exists. So they started doing the measurements to make sure their trains could keep getting through, to look at how much snow normally falls and how much they could expect. And in 46, when the lab opened, we took it over and kept doing that. But in a time of global change, we don't want to just be monitoring and adding bars to this plot. Sure, it helps us do a lot of work with our climate and global trends that are going, or in the climate trends that are going on, but it's not helping much. So recently, instead of just continuing with these monitoring adjustments, when I came in 2.5 years ago, I wanted to step back and take a look at how the lab could better improve not just water in the Western US or the snowpack, but also push forward the science as a whole. And my predecessor, Randall Osterhuber, set me up for this because the lab was kind of an open book as far as what could be done with it. When he retired in 2019, he left a big legacy of helping teach avalanche courses. He left a big legacy of helping all kinds of people do research. But ultimately, at that time, the university, unfortunately, decided that they weren't seeing any benefit and wanted to shut it down. And so Rob Rue, Professor Rob Rue, he's here on campus. He does trace gas exchange research. He held a town hall in early 2020 to say, let's save this amazing lab that's done all this work for decades, right? And at that point, the university met with the California Department of Water Resources and various universities, and they said, okay, we'll keep it. But we want you to write the position description, and we need a different perspective on things. And that was January 2020. We all know what happened shortly thereafter. COVID hit, everything went on a hiring freeze, and I was in Australia, finishing up my PhD. So eventually, they came off the hiring freeze in late October of 2020. And I did an interview, and they said, cool, come up here. I said, you want me to move during the global pandemic? And I said, all right, you can take like 4 months. So that was in December. I came up here in April 2021 and really looked at how the lab could impact hydrology as a whole, and came to 3 big things that needed to be addressed for us to really more accurately manage our water supply and help us out moving forward. I want to make sure I'm on time. The first of which being monitoring and operations, which is something that was partially done in the past, but not completely. Second of which being instrument design, that was always part of the Snow Lab's history. And the third of which being modeling, which we had never really engaged with before. So the first here, one of the wonderful things about science, and especially weather science, in my humble opinion, is that people get excited about it. Down here on the coast, when you get those atmospheric rivers coming in, everyone's talking about it, right? Whose tree fell over where? What was the maximum wind speed you thought happened? What's the forecast looking like? People naturally want to engage with weather, and especially so in one of the snowiest places in the continental US. In fact, kind of sidebar, but aside from towns that are literally on mountaintops, Soda Springs, where the lab is located, is one of, if not the snowiest location in the continental United States. It beats out Valdez, Alaska. It beats out most of the other mountain towns throughout the Rockies. Again, on average, we get 30 feet of snow a year. That's a lot of snow. So people love this type of information, and we keep tabs on it. The people on the summit live and die by weather information. Realistically speaking, with big weather systems like the ones we had last year, those end of December atmospheric rivers shut down everything for about 3 to 4 days. There was no road access, power was out, no internet, anything. And so these people that live up there and around Lake Tahoe, it really does depend on what the forecast is. And so coming in, we realized that, and we said, you know what, we're already doing these forecasts for our own purposes to figure out when we need to measure this snow, how we can keep our crew safe. Why don't we start putting them out to the public? And then that kind of became some of our operations perspective. And in addition to that operations perspective, luckily, as that went on, people realized that Snow Lab knew what we were talking about, maybe barely at times. Who can actually tell you what the weather forecast is without a crystal ball? Anyway, but realistically speaking, we started putting out those forecasts, and Caltrans have now picked them up. The operation, the California Office of Emergency Services now uses them. They've become a big part of what we do. And as far as the monitoring portion goes, and the operation as well, that left image is the reservoir levels as of yesterday, I think it is, around the state. So earlier this year, we had this massive storm, right? We had, or this massive winter, I should say, all this snow. It immediately turned around from we're gonna all die in fires to we're all gonna die in water. And even though most of us in the water world knew that flooding was not really a concern, the news headlines said otherwise. And so we went, okay, how do we quell this? And the Department of Water Resources said, let's do weekly reservoir operators meetings so that they can be briefed and figure out how much water is going to come into their reservoirs and they don't have to freak out. So that's part of our role now too. The snow lab actually provides forecasts on the snow melt and the quantity and timing of that so that the reservoir operators can adjust their operations for their reservoirs as well. So that's the first part of our monitoring and operations. The second part is what we do on the site on a daily basis. On the left, top left there, you can see my hand sticking a ruler into the snow. Believe it or not, that's the most important measurement we take on the site to this day. There are one of only a few sites in the world where there are actual observers that go out and record the snowfall over a certain period. So we go out at 8 a.m. and 4 p.m. every day, stick the ruler into the snow on that board in 4 spots, take an average, take samples of the snow in 4 spots, take an average to get the water content in the new freshly fallen snow. And then we wipe off the board, wait for it to pile up and do it again. Those measurements are incredibly important, and I'll come back to that, but it's one of those things. We have all kinds of different projects going on, brand new technologies going on, and yet that's still the most important one that we offer. On the top right there, more monitoring, that is Marion, doing measurement in a snow pit with me earlier this year. That was that when CBS was there? So CBS wanted us to dig a snow pit. Well, they wanted to dig a snow pit, turn it into Marion and not digging a snow pit. But we were looking at the conditions of the snowpack there. So you can see, hopefully in her little triangle there, in her snowpack cutter, that there's different layers in the snow. And those tell us a lot about if we get rain falling on top of snow, is that going to move laterally in the snowpack, or is it going to percolate straight down and into streams? Because if it moves laterally, it can build up to a point where it can release all at once and cause flooding. So we go out there to do those measurements on a regular basis to get things like snowpack temperature, layering, density, all kinds of good stuff, crystal structures. Now, the measurement on the top left occurs whenever new snowfall comes down. Doing snow pits with Marion or something similar, that happens generally once or twice a month. And then when we turn around and say, okay, but what is this monitoring and what do these forecasts really help us do? It really comes down to event decision and support and research climate trends. So on the left there, you can see an image. This is from a paper that Ann Hagley at the Desert Research Institute wrote. I'm a co-author on that paper, and what we did is we took data from the snow lab that looked at periods of rain falling on snow, the response in soil, and the response in streams, and developed a decision-making chart for forecasters to figure out whether or not they should be concerned about flooding during rain on snow events. So that used data from the snow lab to create and uses data currently from the snow lab to actually do these forecasts and have help the decision makers really do their jobs. On the right is an example of the climate trends we've been looking at. We talk about snow being incredibly important because it's its own reservoir, right? We don't have to wait for it to, we don't have to really manage it a whole lot because it flows downhill on its own. It gives us constant supply of water compared to rain, where it falls, immediately needs to be trapped in a lake or reservoir for our use. And don't get me wrong, we collect snow water in reservoirs as well, but having both in the system, rain and snow, helps us out a lot because we don't have to have snap reactions on what to do when we get a big rainstorm. Do we need to release water from a dam to make room for potential flooding? Or do we keep that water in and hope that we're okay? With snowpack, it comes in so gradually, we don't have to make decisions like that as much. So when we talk about climate change at the lab and some of the data that we've picked up, and we look at that right image, basically what this is telling us is that we're going to maintain roughly the same amount of precipitation, but that it is changing to rain quickly. And we were able to identify the months that's happening. Of course, our season is shortening, so we're getting more rain in months like October, November, May, and April. And oddly enough, we're getting a lot of midwinter warming that's contributing to rain in January too. So this is the type of thing that our monitoring and data collection really helps us out with as well. In terms of that second silo, instrument design, this is fun because it's all over the place. This is one of my favorite projects in the lab right now, but it's one of the most simple too. Who here has ever worn a mood ring? You've done this site. So realistically, this is a project with the California Department of Water Resources to look at the material that are in mood rings. It's called thermochromic pigment. It changes color based off of temperature. Based off your mood, sorry. But based off of temperature, right? So this thermochromic pigment can actually be picked for the temperature that you want to change at. Right now, we are really, really bad at measuring the temperature of the snowpack. And spoiler alert, the temperature of the snowpack dictates when it will melt and how easily it will melt, right? We can't put structures in the snowpack because they break very easily. I can tell you there were a number of cars and semi-trailers crushed on the summit this year from the weight of the snow. So we can't put things in it consistently, but what we can do is pick a threshold for this pigment. -1 degree Celsius, just basic to start with, and then coat an avalanche probe in it and stick it into the snowpack to see whether or not that snow is what we define as ripe or ready for melt by being above -1 degree Celsius, or whether it's below it. Very simple project, but has enormous implication because if we can get this to work, this will be done at 265 sites around the state. And even though it's just a basic binary thing, we can still feed it into our water models that will help us more accurately predict our inflows. On the other hand, we have this project, much more complicated, with NASA JPL, done with in collaboration with Manuel Dorado's lab. This is something that we engaged on earlier this year with a field program. You can see us doing another snow pit. I'm at the bottom there with a little white cap on in the snow. Believe it or not, this was not at the height of the season. This was only in February. We still had 2 more months of snowfall to go. You would have lost me completely in there. But I'm taking snow pit measurements to compare to what that aircraft is seeing. That's a NASA JPL plane that uses a new type of technology called GPS. Just kidding. It's called P-band radar. It's a very high precision GPS that the Navy uses. And it was determined by our colleagues at NASA JPL that this P-band radar is easily attenuated by snowpack and the water in a snowpack, which means that if we can get a measurement of the signal coming back off the planet, as well as the signal going into the snow, we can do a simple calculation based on the two to figure out how much water is in the snowpack. The problem with that being, GPS satellites only bombard the planet with signals, they don't actually receive it. So what we did was there was an antenna mounted on that plane to receive the signals. Just as the antenna underneath it, this big square looking thing will be mounted at the lab. And we provided ground truth for that antenna in a pilot project. The proof of concept was successful. And at this point, we are in competition with one other project at NASA JPL for a $300 million satellite program to launch receivers in space that would, for the first time ever, give us worldwide coverage of the amount of water in our snowpack. Not snow depth, because snow has different densities, right? So if we use LiDAR, if we just use basic depth products, it doesn't really help us, but the actual water content, that's what we're interested in. So from painted on an avalanche probe, satellite missions with NASA, right? Wide range of cities. So this one is something that we engage in a little bit less and is new to the snow lab, but we've done in the past as well, and that's weather and snowpack modeling. So on the top there is a very basic graphic of all the things that can affect our snow melt in terms of energy. We have solar radiation, right? The sunlight that's coming in and being reflected by the snow. We have infrared radiation from things like trees and clouds. We have turbulent fluxes, which are driven by a combination of wind and temperature and relative humidity. And we have soil heat. Believe it or not, the ground melts the snow too, gives us what we call basal melt. And so this is all occurring nonstop, right? And it's very hard for us to measure this accurately in a broad area. So we have a tendency to want to model that. So what we tend to do with our models is we'll run something called a model like iSnowball, which is a fairly common one at this point. And it determines the physics of the snowpack based off of the weather conditions above it, as well as things like inputs from the Airborne Snow Observatory, which is an aircraft that scans the snow with LiDAR to get how deep the snow is. It ingests all this data, and then it spits out what it expects the snowpack to do in terms of melt, in terms of morphology and evolution. And unfortunately, we don't really have ways to verify what those models are putting out. There have been studies that have kind of done it, but we don't have ways to verify it consistently. And so fortunately, as part of our work with the Department of Water Resources, we've installed that tower on the right-hand side, which, by the way, to the floor of that tower is 25 feet, and the deepest snowpack we've ever had is 20 feet. So if you can imagine where that falls on that tall tower, it's pretty remarkable. But that gives us a full workup of the snowpack energy balance so that we can go to these models and say, how well is this working? How much do we need to tweak it? Are we actually seeing the snow melt that we're expecting to? Because we're running these things not just over small areas, but we're running them for massive catchments. Catchments all over the Sierra Nevada, catchments all over the Rockies. And if they're wrong, even by a little bit in terms of energy components, it can mean a lot of water that's potentially going to evaporation that we're expecting to come into our reservoirs. So we do this snowpack modeling and contribute our data from the lab to help verify it. Now, another type of modeling, who here has been upset with a forecasting bust for snowfall? Anybody go snowboarding or skiing and they're like, oh, we're gonna get 16 inches, and you end up getting like 3. Like, what in God's name went wrong? Weather models are notoriously bad at a couple different things. But one of them is figuring out just how much snow is going to fall. We're pretty good at knowing how much water is in the atmosphere. But the thermodynamic profile of the atmosphere determines how much snow you're going to get. For instance, in an average condition around most of the world, you can get a 1-to-10 ratio. So for every inch of water in the atmosphere, precipitable water, meaning it can fall out of the sky, you get about 10 inches of rain, or of snow. So it's a 10-to-1 ratio, but it depends heavily on temperature. In Colorado, where I grew up, Champagne powder, that's 22 inches to 1 inch of water. In Antarctica, it could be 30 or 40 inches of snow to 1 inch of water, because it's all different densities based off of temperature. And unfortunately, our weather models are really bad. And the National Weather Service will be the first to tell you. And this isn't so much a problem with water and us identifying how our water is going to change with climate change or how we're going to manage it, but it's more so a problem of transportation, of safety, right? When we look at forecasts, Caltrans is depending on them, airports are depending on them, and if we say, you're going to get 8 inches of snow and they get 16, it's a big problem. I-80 shuts down, emergency services can't get through. We have things like in San Bernardino County where some of those people were waiting up to 2 weeks for help earlier this year in those massive winter storms. So when we talk about the modeling here, us going out and sticking our ruler in gives us something that snow liquid ratio, 10-to-1 or 4-to-1, because we're also recording the amount of water in the snow. And that water then goes to the Weather Prediction Center out in Maryland that goes, our models said that it was going to be this. Clearly, that's not the case. We need to adjust X, Y, Z. And so that's another area where we're really helping with modeling efforts. We don't run a lot in-house with the Snow Lab, but the data we collect is actively involved in the model. Now, I think I'm coming up on the end of things, which kind of works out well, but in terms of all of these things coming together, these are the 3 big things that really impact our water management. So when it comes to monitoring and operations, it comes to instrument design, it comes to modeling, we need all of these 3 things working together, because the better instruments we have, the better models we have, and then the better monitoring we can do, and then the better forecasting operations we can do. And all of that comes together to allow us to better manage our water resources. And that's the goal that the lab is focused on, so that we can forget about these audits. And instead, unless there's something catastrophic going on, you and I can just have a relationship with water where it's coming out of the tap. Because that's the goal. The less that us as common people have to think about where our water is coming from, that means the system's working. It's not ideal. Coming from a meteorologist and hydrologist, I'd love it if everyone always knew where every drop of their water came from, because you would have that more intimate relationship. But it's not until we enter some type of crisis that most of us tend to think about it. So the better we do these things, the less you'll think about it, and the more it's less, then the less of an intimate relationship you'll have. So that's overall why the Snow Lab's engaged in what it is. And we've really broadened out away from just that monitoring. Because we are in a time of transformation, we're in a time of transition, we're moving into a climate that we haven't had to deal with before, and it's posing new challenges. And so therefore, we have to focus on these areas, because whether or not we want it to, it's going to change, and we're going to have to play catch up and fight for every drop that we can get. Now, with all of that being said, there are a number of ways if you're interested in keeping up with the lab. We are on social media. We're on Twitter. I refuse to say X. We're on Instagram. We're on Facebook. We do our forecast there. We update every morning with our measurements. We also put out any type of important information there. As Marion mentioned, we have grown some type of media personality, media frenzy around us this last year. So if you watch one of the major news networks around the Bay Area, chances are you'll see us on there at some point, charging through the snow. But if you don't want to go through the hassle of watching TV, cssl.berkeley.edu. We update all our numbers daily, tells you where we're at in terms of percentage of average. We give a broad area overview. So if you're like, I'm going skiing in Mammoth today, how much snow did they get? It'll be on that. And then also, new this year, we have, as part of that new system that we installed to help verification of our models, that energy balance system, we have a live webcam that I am ashamed to say is down today for the first time in its existence, but I promise it'll be up again tomorrow. It will allow you to keep an eye on conditions up there. You would not believe the number of inquiries that we got. I just want to watch the snowfall. And while we installed it partially for that, we also installed it because it helps researchers a lot in determining what's going on. When we think about rain on snow, we want to know the moment it transitioned from snow to rain so that we can start mapping the impacts that's going on throughout the hydrological cycle at that point. So we have that available for you as well. That's it for me. I think 4:27. That's pretty decent timing. This is my associate Gabe. The lab is to the top, to these windows, a 3-story building. That's how much snow we had last year. It was a unique winter for sure, but that's where we're kind of at. It was a high-level overview. I'm happy to talk about specifics, but that's kind of what we're facing in terms of water in the West, the improvements that we're trying to make, and how the snow lab fits into it. Cool. Any questions? Yes.
Thank you for the brief talk, by the way. One question is, say you measure the exact snow lab, how do you take that into the then predicts how much will be in the reservoirs and elsewhere in the California, or is that snow all coming from that area?
Yeah, that's a great question. So this comes to the spatial representativeness, right? I briefly mentioned the Airborne Snow Observatory, which is a plane with a LiDAR that scans underneath it. There's only one snow lab. One of the reasons why we're sought after by collaborators is because we have a staff that's on site basically 24/7, 365. But we do have automated weather stations that don't have that same luxury, but do provide point measurements at the top of other catchments, right? So we have about 250 automated weather stations throughout California, as well as 265 sites that teams hike into once a month from January through May to do measurements of the water content in the snow. Putting those together gives us a pretty solid map of the snowpack we have and what various reservoirs and areas can expect to see. With that being said, it's still a small pointed space. So coming back to the Airborne Snow Observatory, they scan with LiDAR. We combine that with our in situ measurements on the ground. That then gives us some type of idea of the density and the water content, and then we model the entire catchment using ice snowball that I showed earlier. So it's really a collaborative process between all these different organizations to bring this one product together for each catchment. And up until recently, these flights over these various catchments were only flown on very small scales. There was only one plane based in Mammoth. It would do maybe 2 or 3 catchments a winter. Now there are 3 planes in various states. They're doing basically the entire Sierra, parts of the Rockies, and it's really helped us with determining how much water is coming down when in the past we only had a single point. So, but it's still part of everyone coming together to collaborate. Other questions? Yep.
Very good work. I'm curious about the stream part of the story and with the record ecology. And so do you have sensors on the stream that would allow you to see and all these like rain and snow events, like how fast they turn into, or have a control flashiness or like yeah, some changing flow?
Yeah, so did everybody hear the question? Okay, just want to make sure. So realistically, the question, we have in the past had stream level sensors. In the early days of the lab, they had a dam and then a large weir that they had built. Coincidentally enough, like 18 months after they built this big, beautiful weir with these observation booths on it and everything, a rain on snow that occurred and destroyed the entire thing. So we have had stream level sensors in Castle Creek, which is at the snow lab. We've gone a couple years without them, but it's part of that new instrumentation system. It's called the sky to stream system because it measures from the moment it comes out of the sky until it goes downstream. So we do have a new stream level sensor in there. We are working in terms of water quality with Monica Arienzo at the Desert Research Institute. She's doing various work with microplastics and PFAS in terms of pollutants and things like that. But yeah, we do keep an eye on the stream flow response to these events because we do, ultimately, if it rains on the snowpack and it doesn't change anything in the stream flows, there's not much to worry about, right? But we really want to make sure that we can identify when that's going to change and quantify how much it is going to change. You had a question?
Yeah, thank you for the presentation. I just had a couple of new questions.
Yeah.
What's the spatial resolution on this? I like this other question about what would you like to have for spatial resolution?
Yeah, that's a great question. So spatial resolution on the plane, if I recall correctly, I think it was 3 meters. I know that's similar, if not the same, to the Airborne Snow Observatory as well with our LiDAR, but I think it's 3 meters. As far as the satellite program, I'm not as much on the satellite side of things, as much as the verification and in situ measurement side, in terms of, managing the field programs on the ground. But I think we're shooting, realistically speaking, I think we're shooting for a similar resolution. It would be very interesting, to say the least, because once you start to, put various aspects and elevations and latitudes in there, things can kind of get muddied. But if selected, this will be the first comprehensive measurement of snow water equivalent throughout the mid-latitudes around the world. The program that we're up against is looking at doing water content at the poles only. So I'm hoping that because we're doing it in areas where population is directly affected, we have a leg up. In terms of ideal remote sensing resolutions, I think there, how long is a piece of string? For my purposes, I would say 1 meter resolution is good. You're not going to get a whole lot of change even in the micrometeorology over 1 meter. And canopy effects can be introduced from trees and things like that, but I think 1 meter would probably be good. Temporally, it really depends on what we're talking about. If we're talking cold climates like the Rockies, where we're not worried about rain on snow events, probably 6 hours would be a good temporal resolution. If we're talking, in terms of water resources at least. If we're talking about the Sierra, probably better to be an hour or even 30 minutes because of how rapidly conditions can change.
So.
I don't know what the temporal resolution of the satellite is gonna be honest with you. JPL has, Simon has, at JPL is primarily been the one dealing with that and is more aware of the technological limitations than I am. I think we're probably on daily to sub-daily resolution and probably because they're gonna be multiple orbiting satellite, I don't think they're gonna be geostationary.
Yeah, I had a question, so after someone gets the project to start implementing this, like all this new infrastructure to models, how soon do you think that those models or those monitoring operations, all those, how soon do you think that would start to translate to the water management?
Yeah. Again, another trend. These are all great questions. So realistically speaking, transitioning technology to operations, I think for any field is somewhere where we know there's a bit of a sticking point, right? There tends to be a big division between the research and the actual implementation and management that coincides with that implementation. So as a result of this audit that was carried out on DWR, and the fact that they took into account or basically concluded that climate change is not being represented in these models, it's really lit a fire under them to get new things implemented as soon as possible. So for instance, we're working on developing a new sensor to look at snowpack temperature, like I think I mentioned. Part of that proposal with DWR was us saying, we can have a 3-year turnaround with this for you to implement in the models. That is really kind of unprecedented, assuming we can get this, have this work the way we want it to. So potentially as fast as 3 years. Most of the time with the new technologies and the measurement systems, implementation, takes anywhere from closer to 5 to 10 years. A lot of the things that I did at the National Center for Atmospheric Research in Colorado, those were 10 or even 20-year projects, working with people like the FAA on just replacing sensors. So it's been identified as an issue, and so the new term that we throw around is research to operations pipeline, because we want anything that's promising that can help, we want it in there as soon as possible. So right now, we're hoping a max of 3 years with this new project with them.
Is it in 2025 or 3 years from now? Or?
So it would be. So the implementation of the first sensor for that cold content would be installed, assuming all went well, in probably 2025, and the full implementation would be a year or two after that at the 265 sites around the state, assuming all went well. Yeah.
At the beginning, you mentioned the problem that comes with an average down also how difficult it is to do forecasting snowfall and how different the years are. So my question is, how good are the forecasts we have at the moment, and how good are maybe models for forecasting like future climate conditions in the Sierra Nevada and maybe also snow mountains and snowfall rates?
Yeah, so as far as there's definitely deficiencies in the modeling. Deficiencies are unique because it comes a lot of it comes down to a lack of computational power. Manuela said we're targeting 1 to 5 kilometer on the satellite. Sorry, I just saw that. So as far as modeling considerations are concerned for weather, it comes down to computing power. We run WRF, which is the weather research and forecasting model. You can run that with a resolution of anywhere from 5 centimeters up to the entire planet, but there's a trade-off, right? If you're doing 5 centimeters, you're limited by the number of points that you're trying to scale up to. So if you do Texas at 5 centimeters, you probably only do a couple time steps, even on the world's fastest supercomputers. Whereas if you scale back to just 1 point in Texas, and then put, 1 point in every state to a much broader grid, you can do a lot more time steps. And so the fact that we can't necessarily forecast near-term conditions doesn't really have anything to say about necessarily climate change in those models. Because effectively, we just have a set number of points in time and space that we can resolve. If you space those out further into the future climate, decades, centuries, you're gonna get less and less precise. So you get more error in terms of, is Berkeley gonna get less or more precipitation, right? But you'll understand the global dynamics further out. But there is a give and take relationship there, so. Yeah, it's realistically, I say to everybody that asks this question, the answer at some point is quantum computing. The more, because right now, the strongest supercomputers we have deal with petabytes of data every second. These are the computers we use to run our weather models and our climate models. It is actually, I was told this by a computer scientist at Australia's National Computing Infrastructure Program. It's actually simpler to model the universe beginning into the current point in time than it is to run a climate model. So it just takes so much computing power that there is that trade-off. So we can do short-term really well in very high detail, or long-term very well, but broad. That's kind of the trade-off. Does that make sense? I don't know if I answered your question. Okay. Any other questions? Okay, cool.
Yep.